pay for the web hosting costs. So, in all seriousness, with that, it is my honor to introduce Naras and Anqi, the developers of CVXR, who have done truly phenomenal work as a kind of two-person development team with keeping up with some of the one of the most impressive implementations of DCP that I think has always been more or less caught up with us, despite how much less manpower they've had over the years. So with that, it is my honor to pass the microphone to them.
Okay, well, thank you very much, Bob and Steve, for having me here. And so CVXR is CVXPY, and indeed the first version that we released. CVXR is a sister project of CVXPY. It is the first version we released in 2017. Hello, checking 1, 2, 3. Okay. And since then, the work was mostly done by Anqi, who wrote the version of CVXPY that was current then, which is around 1.0 or some 1.1, something like that. And today I'm going to talk to you about development plans for CVXR because, as Parker alluded to, we only have 2 developers, which is me and Anqi. How are we ever going to keep up CVXR? Right? Okay, well, we live in the modern world. So this is what I did. I said, yeah, -4 CVXPY version 1.8.1 is a returned version. Put it to R, tell me we are done, and it's. And it did it. But I thought it's done by it. I'm joking. So, actually, what happened was, this is a joke, and it's a hard work. I'm going to give you a progress report. So the mission is, if you have the R port of CVXPY, you have to you're falling behind CVXPY in many ways. And now we want to sort of make use of developments in AI to see if we can somehow catch up. And also, not only that, keep up with CVXPY. It's not enough to catch up because we have the same problem again. So there are a few things that actually have made us optimistic. One of which is this new facilities for new AI development. And there are some new facilities in R itself that actually offer hope of catching up. So let me tell you a little bit. I know that here we are mostly Python geeks here. So I'll tell you a little bit about R. So for those who don't know about R was created in 1993. It's a descendant of the S language, and which was developed at AT&T Bell Labs. And it's the #1 language for statisticians and biostatistics. It's a lot of biostatistics work, including the whole biochemical targeting thing. And there are over 20,000 packages. And by the way, these packages are curated by humans. It's not PyPy. So this things go, and the wheels sometimes don't work, or you have to jump through some hoops and so on and so forth. So this is actually human curated stuff. And then there's a whole bunch of infrastructure on it, as I said, bioconductor, IDverse, and Shiny. All of these have had impacts on Python. Pandas come from R data frame, all that stuff. Of course, R is a little unique niche language in the sense that it was not developed for programmers. It was developed as an exploratory programming language that people wanted to do EDA, exploratory data analysis. So which means there's a lot of interactive stuff. You modify things, you want to see whether this model fits or not that. Play around with it, and then decide what you want to do. But it has grown, the R version, grow into one which has actually very interesting functionality. In a functional language, almost functional, in the sense that everything is done via functions, and of course they don't need have side effects. Not quite true in R, but almost. Also does multiple dispatch. So it's do polymorphism and so on. So it's actually pretty advanced niche things it has. Everything that exists in R is an object, which means that there's nothing really atomic. That's the sense of bits and bytes and so on. Everything has got some metadata. And everything that happens via a function. So how would you do OOP in a case like that? So there are lots of things like that, which means people decided developing object. So here's a quick run through a few features of R that you may not have heard of. So think of this as, introduction to R on steroids. So R has 4 major object systems. The first one that came with R is something called S3, and it is just a gentle intermediate. You create an object, you slap on a class name to it, everybody's supposed to pay attention to it and behave nice. And that's not something that guarantees real outcome. Then came something called S4 on top of that, which tried to make things a little more formal. And it's actually quite formal and strict. You can define generic methods. You can pass on any objects, and the things get dispatched to the right method based on the object class. So that's S4. And then on top of that, there was R6. I won't even go into that. And finally, now we have something which is 2024. This is the new hope, because this thing at least matches the kind of OOP that you actually see in platforms of class definitions, methods, and things like that. So this is what you're going to sort of piggyback on. So if you wanted to program in S4, you'd have to write something like this. Suppose you take the ads atom, for example. You have to set class, define a class, and then you actually have to define a function that actually a factory function that generates the class. And then you have a whole bunch of methods you define for all the DCP stuff. Okay? Now imagine doing this 100 plus times for each atom that CVXPY already has and might have in the future. Impossible. I don't know how Anqi did it, but she did it. This is the part that she implemented it. Okay, talking about R packaging. What does an R package consist of? It consists of a structured set of folders organized as follows. So the description contains who the authors are, what dependencies there are, etc., etc. The R directly contains all the R code. The SRC can contain C++. R always had connections to C and things like that. C++. It's always been there. And then there's documentation, there's tests and vignettes and things like that. So this is the simple structure of an R package. The problem, though, is that CVXPY is a deep directory tree. It naturally occurring file captures, right? So R packages require a flat R directory. How do you flatten without collisions and things? So the main thing is when you even try to approach, using some kind of tools to do this, you have to think about all these organizations. Otherwise, you're going to easily get into trouble. So one of the things we did was develop this thing called mirroring CVXPY. So we've decided we're going to mirror the CVXPY tree no matter what. For that, develop an isomorphic tree like this. So it's a tree that's exactly like this as it's in CVXPY. And every file starts with a little bit of annotation that says which CVXPY source it refers to. And then you have a script. It takes all those things, flattens it to the one directory, but it also has to manage what's called the load order, typically the collate order, as it's said. So which means that you have you can number them. So we number them 0, 1, 1, whatever it is. And you have one script, it's automatic, it's reversible. So this takes care of this problem. Next, S7. How does this object system look? Well, again, it has a new class, a class constructor, and then basically, again, you define all these methods. Remember, R is functional. It means they're called functions. But it's at least a little more recognizable than S4, which is a whole bunch of stuff around. And in fact, it's actually, if you look at code, it's not very different from Python. You'll see very clear isomorphic structures. So it's clean, compact, one file per app. So here we go. There's the CVXPY code. That is the CVXR. It's a clear, almost one-to-one correspondence. AI can do. Right? So again, we tried this. So we thought, okay, let's try a systematic AI-assisted rewrite of R from scratch. With guardrails, you're going to have an isomorphic, there are some mandatory rules. You have to have an isomorphic file structure. You have to have some architectural constraints. About 150 documented design decisions went into it. And of course, the proof of the pudding is in the test. You got to match every test that is in CVXPY. Otherwise, I don't know what I'm doing, or there's no guarantee. So there's rigorous test mapping to CVXY. So here's the journey. We started at Foundation 95, simple tests, and so on. And right now we are up to 7,000 tests. Okay? So that's where we are. So what are the design choices that matter? So by the way, I'm saying I'm trying to minimize the code writing in this part because there is no way I can be or Anqi can do this. So there are some structural choices. For example, again, as I said about the isomorphic file tree. Oh, interestingly, R has always had operator overloading, which is perfect for us because the new S7 plays very nicely with the old existing R3, so we could easily overload all the operators and so on. The C++ bridge is unchanged, same canonization that we have in CVXR. We also have cache for doing, basic evaluations. We have design conventions documented, and every decision we recorded. Testing keeps us honest. 3,247 test lots, each annotated again. Because when a test fails, I don't want to go hunting around to see which test failed, which CVXY test it corresponds to. Okay? Again, AI can do this very well. All these kinds of people. Cross-reference with CVXY tests, with validation scripts to find gaps. So here it is, coverage. CVXY parity is 514, R-specific 2,997, documented non-applicable. So some of the atoms not yet implemented, of course, and some of these are not ready yet. So here's the progression. Solvers. How many solvers have we implemented? We started with phase 6. It's only at phase 6 we got something functional. Then we move down. So we have now 13 solvers. And then, of course, features that old CVXR never had. We actually didn't have DGT, didn't have log space transformation, or DGT atoms, DTT. DTT was there, but it was a crooked way, half implemented. No DQCP for sure. And complex numbers, again, half implemented, something half baked. We now have it. There are 50 canonical geysers, permission variable, warm starts. Again, warm starts were working only in some cases. Logic atoms, perspective, finite set constraints. So the question is, does it actually work? Wait, let's see. Here we go. Here is a set of docs. Sorry, I have to put on my glasses to see the screen here. There we go. So this, I can move this over there. Okay. So this website tells you, is it, sort of again, website for CVXR that details all the stuff that is there. So here we are, 1.8.x. And, all the examples are already sort of written up and they all work, getting rendered. And okay, so coming back here, in the docs, what we have is all these experiments that we borrowed from CVXR. And by the numbers, we have 7,000 total tests, added tests, all of these, 100 plus atoms, canonicalizers, and so on. And of course, the numbers are different because of the fact that we have a different way of counting these tests and so on. Performance. The S4 had a lot of overhead before. What compiled in, say, 1.16 minutes, now compiled in 2 milliseconds. And look at the memory footprint too. Okay, so improvement there. And so it's 300 times faster, less memory. Okay. And here's a simple lasso example, for example. So we have this increase in problem sizes. And as you can see, this is what we expect. We expect the canonicalization cost to be constant, except that the cost of the solver it was increases and so on. So everything is looking okay. And there's room to grow. So we have BPP fast path, parameterized resolve. We have direct solver calls if you want. And we have profiling that we actually reveal some hotspots that I think should be improved. So we got correct first. Speed comes next. Little more work to do on speed. So where are we? Okay. Okay, that's where we are. I have one more thing to say, though. I mean, I'm not done yet. So let's see. Here, because I think that I don't want to be because I think I've done this without work by other people. Okay, so keep me on. Let's keep more slides. So I think this is the way we plan to sort of keep up with CVX. This is the way we plan to keep up with CVX. It works. Point to a commit, and you want to make sure there's no regression. You have a fixed scope. You have breadcrumbs that lead us back where we want to look at things. And then the same process that actually helped us will go going forward. And so this is going to be going soon on our plan. And there are a few things that are deferred here that I've said before. In the interest of time, I'll go quickly. But I want to say a few things. This is the most important step. This is what made it work. On the shoulders of giant and the disciplined architecture. And I must say, the thing that I learned most was really to sort of focus the design document to really make sure this followed my instructions very well. And I actually looked at every day of code. Yeah, I did do that. My wife said I didn't sleep because I was so excited about this. So 179 comments in 10 days. And so that's right. Shows that, well, close enough. Up to that. But clearly, my main thing is I didn't want to actually shout out to Anqi. I don't see how I could have done this work without her. Unbelievable work on CVXPY, the previous work on CVXPY. That's what led me to do this. So I think that AI tools can help, at least in projects such as this, which is, because it has already been established.
on Wednesday, as we were doing the walkthrough to make sure we had the venue all set up and we were planned for today, Naras told us that we would be surprised by his presentation because he had a cool announcement. I never in a million years would have been able to guess what that announcement was. So I also want to take a second and say thank you to Naras for the incredible help organizing. We would not be here at Stanford. We would not have really been able to get any of this together without his work. So I want to take a second and ask him to give him a round of applause for his phenomenal work.